Alright, are we live? Hello? 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 Nice. Sweet. Hey! Oh, I was gonna do something before I started this, but well, not do that now. I wanted to program something else today. Just work on the problem. Nothing too interesting or exciting or what have you. Just work on another thing. Yeah, let's get to it. All right. So okay, let's do that. So the problem is going to be shortest word distance 2 from Leetcode. And as you can see, I'm practically blind, so I have my face pretty much crammed against the computer here. All right. It says, let me see what you guys can see. Yeah. Okay. Shortest word distance 2. Design a class which receives a list of words in the constructor and implements a method that takes two words, word 1 and word 2, and return the shortest distance between these two words in the list. Your method will be called repeatedly, many times with different parameters. Assume that the words practice makes perfect, coding makes input. So word 1, coding, word 2, practice, output 3. Coding, practice, 3. Shortest distance between these two words in the list. 1, 2, 3, 4. 1, 2, 3, 4. How do you, what does that mean? I don't understand. Makes coding. 1. Like literally the indices, is that what it means? Like we took the difference between the indices and the absolute value of the difference between the indices. Find the minimum where you have duplicate words in the list. Is that what that means? Word 1 and word 2 makes coding. You may assume that word 1 does not equal to word 2, and word 1 and word 2 are both in the list. I think that's what that means. I think that's just, there's a, well, let's think about this before we start coding it, because I don't necessarily even know the answer. I don't even necessarily know what they're asking. Let me think. So you've got a whole bunch of different words in a list, and you could, let's say if you didn't have any duplicates, is this a simple question, simple problem? I think so, right? Because each word would have an index associated with it, and you can just create a map from your, basically the reverse mapping. So given the string, you take an unordered map of strings and map them to their indices, and then you would say, okay, given those two words, you can take the difference, the absolute value of the difference between those two, map the word to their indices and take the difference between the indices. And I believe that's all you need. Excuse me. Yeah, I think that's what that, from like coding to practice. Practice, you have, looks like 1, 2, 3. Yeah. Now, what makes this tricky and not quite work that easily is if you, so that would be constant time each query, and it would be a linear amount of storage space, or pseudo-linear, because the string size matters. But which is quote unquote linear with respect to the number of words, and then also linear with respect to it's the linear amount of space and linear preprocessing with respect to the number of words, and then constant time lookup. However, things get kind of complicated when you consider that you could have multiple indices for a particular word. And now if you have multiple words, if you have your query, your 2 words, in other words, you could consider both words having actually multiple indices associated with that word rather than just one index. These are obviously all being unique, right? Because the indices are sort of by definition unique. So if you had like 1, 2, and 5, and 3, and I don't know, 3, 6, and 7, right? 1, 2, and 5, 3, 6, and 7. You would want to find between those 2 lists the smallest difference, right? And that's kind of interesting. That's an interesting question. I think you could still make it pretty fast to do that, but that is an interesting query. Is like if you just had a list of numbers, 2 lists of numbers, and you wanted to find the 2 numbers with the smallest difference, absolute difference. I've seen that. That's a question that comes up. That comes like a concept that comes up. I've seen that a few times in different questions. That creates kind of an interesting scenario, algorithmically. That property, right? Finding the 2 elements that have the smallest difference from some 2 lists of elements, or usually numbers. How could you find that efficiently in general, or at least just in this, in general, or in this case, I suppose. They're more or less random in this case. The numbers, somewhat random. You could say, I don't know. It's a good question. What do you do? Well, clearly every number in one of the lists does have a closest number to it. You can, if you have these lists could be sorted pretty easily. You could have these sorted lists and consider them as sorted lists. In which case you can search for, you can do a binary search on each number. Now that's an interesting approach. Not sure how I feel about it exactly. That in theory could solve the problem, right? So there's a few ways to solve this. So one way is for every number, literally find every difference, right? And that would be sort of the cross product of these numbers, and you have to go through all these indices, all the cross products. It's not very efficient, but you can do it that way. Another way is to, instead of doing a cross product, or Cartesian product rather. Cross product's not the right. I keep using the word cross product. I used that in the last problem. I was using that word. It's actually a Cartesian product. Cartesian product of these numbers, and find the pair with the smallest difference, sort of exhaustively. Another way to do it is to actually use a binary search to find the closest number for a given. So you iterate over, like, let's say there's a set A and set B. You iterate over all the numbers of A, and then for each number of A, you can perform a binary search on the set B to find the number that would be closest to A. I believe you can do that, or you can do something like that. And that still doesn't seem very good. It's also not clear to me exactly how you do it. I guess you would find the first number that's larger than A in set B, and then that means that if it's the first number that's larger, that means the number preceding it is also must be smaller if it exists at all. And then you can compare those two numbers to the differences between those two numbers, which would make sense. It has to be one of those two has the smallest difference. Those are the two numbers that are closest to the number you're using as a sort of a key. Let's call it x. So for number x, you search in set B, and you find two values with two indices, sort of I and I minus 1, we'll call them. And so the two values found at I and I minus 1, you compare those to x, take the absolute value of the difference between those two, and take the smaller of those two results, and that's the index that you want. The problem with that, though, the problem there is it's still relatively inefficient because you're looping over every value in A, and obviously you can use the smaller of the two sets to optimize that slightly. So that way the logarithmic portion is over the larger set, but it still seems relatively inefficient because you're looping over every value in A, and then each one of those values you have a logarithmic amount of time that you use. The problem with that so I want to say there's a better way to do that. There's got to be a better way. There has got to be a better way. I want to say there's got to be a way to do it that's logarithmic in both terms. Log of n times m, or log of n plus log of m. That's what I'm looking for. However, it's not obvious how to do that at all. I'm going to think about that some more. Excuse me. My stomach just actually didn't growl, it just moved. Yeah, it moved. My stomach growled. Yeah. Ugh, it's so gross, dude. It's gas moving around inside your stomach and your intestines. It's just moving around in there. Stuff moving around your intestines. Gas and food and liquids and whatnot. Okay, so log of m and log of n. How could we even achieve that? How could that be even possible? I would say for this question, it's probably sufficient to just use the logarithmic search. However, that could be very inefficient. Like if you had just two words over and over again in your dictionary, and you had a huge number of them, so it's basically split in half into two. Excuse me, two words, and so two lists of indices, and they split the list into half, so it's n over two numbers in each list. That means each query is going to take n times log of n, which is n log n time, which is not very efficient at all. Excuse me. Excuse me. Wondering if there's like another way to look at this problem or to think about it. Maybe it's like a graph problem of some kind. Not really. Another graph doesn't really help you that much. Excuse me. Actually, maybe it does. I take that back. Yeah, maybe you may be able to possibly use, maybe, I'm not sure, what's called the, maybe not, I don't know. I'm wondering if you can if you were to group all these indices into one entity, and you got these two different entities that you're comparing to each other now, and somehow you can quickly find out which part of those entities, sort of which node, which piece is closest, if that makes any sense. Really down for a minute. Excuse me. Yeah, I don't know. I don't really have a good, more efficient way to do this than what I've already described, which is not great. That's kind of it's a bit lackluster, isn't it? It's got to be a more efficient way than sort of a log b, we'll call it. A is sort of the size of set A and B is the size of set B. Yeah. Yeah, that is definitely not the most, I guess, encouraging. Definitely not the most encouraging of possible algorithms possibilities. I just think I want to say like other problems, other questions. Sometimes it's possible to prove that there isn't a better way to do it. In which case you can stop, banging your head against the wall, so to speak. Let's think about this some more. Try to think about this some more. Huh. Basically, what I want to say is that there's some kind of data structure that we can pre-process each of these pieces into, and then we would always know that answer really quickly. That's kind of what I'm getting at, where I'm going with this. Obviously, for one case, we just have, you know, two lists of numbers, and you got to figure out, okay, which of these, you know, which pair of numbers between these two sets gives you the smallest difference, smallest absolute difference. That's kind of hard to answer. That is sort of its own problem, I guess. That's kind of tricky to answer outright, in that I think the best way, the best answer I have at the moment is just sort of quote unquote A log B, where, you know, you look at each number in set A, and then you try to use a binary search in set B to find its partner. And then of all the pairs that you find from there, the best one that you found is your answer. The problem with that, though, is that's not super appealing as an answer. Also, where is, got to charge my headset's about to die. Just give me a minute. I'm running out of charge. And so, what, excuse me, what do we think? What do we think about this problem? Is there a better way to do that? I mean, is there even, like, that's the first question. It's like, is there even a better way to do that exists? I don't know that there is. Yeah, because even just generating all of those pairs in the first place, it's going to take you a log B time. Obviously, as you generate them, you can sift through find the optimal one. I'm wondering if there's a way to skip certain numbers, if that makes sense. I don't really think so. I don't really think so. It's such a weird property. It's like if you try to visualize it. It's like the numbers that are closest to each other, but they're from it's two different. They're from not from the same set. Excuse me. It's a very unusual. It's a very unusual property, a very unusual kind of a thing. I've seen it a few times before, though, but different contexts. Maybe you could do it a different way. Maybe you could say for each word you would automatically know. You would sort of have some step where you sort out ahead of time for every index from the get-go, for every other possible for every other index, which index and which word is the closest for that index. And I guess you would actually update. So that's kind of interesting. I mean, that gives you something a little weird, where that gives you kind of like a map of some kind. That gives you like a two-dimensional array, which I don't know if that's particularly good or useful or what we should do. That gives you quadratic time with respect to the number of words. I don't know if that's good either, but basically you would update each pair as you go with like what the optimal distance is, because you basically would actually, yeah, I don't know. It's kind of hard. Like you could say each index has an optimal word associated with it already, I guess. And then you could actually I guess look through those indices. It's a little weird, but I want to say something like there's a way to do this where you can make it sort of logarithmic somehow. Just thinking, how do you do that? Oh no, man, I don't know. I'm running into all kinds of weird positions, weird uncertainties. Like I want to say something like oh man, this is a good question. This is a good interview question because this like really makes someone think. You know, really gets you thinking. How do you wow. Wow. How do you deal with this now? Excuse me. Excuse me. I don't know, man. I keep thinking about it. I'm like, oh well, what if you had every index, for each index you have like a list of words, obviously words that are unique in the in the list don't really count, don't really matter. Well, even words that are unique, it's only the duplicate words where they're duplicates where things make a difference, and then you would have to say that you sort of have this pre-computed notion, I guess, for that particular index. For a particular index and a particular word, there's sort of the other word, right? So there's some index and then the other word, where those other words are, which one is closest to this particular index. And then you can update sort of that general pair of those two words accordingly. And I guess as you continue, you would update all of those different indices as you discover new values as you go, if that makes sense. I'm not sure that makes sense. Oh boy. try to think through this problem. I don't have a good solid answer. This question, if you're given a whole bunch of numbers in two different lists sorted, so it could be sorted, it doesn't have to be sorted, but it could be sorted, and then you want to find, it's not really for each of those numbers. Well, here's something that's kind of interesting, is for each of those numbers, there is exactly one, for each number there's like some symmetry here where for each number in A, there is exactly one number in B that is closest to that number A. In other words, it's unique. Not only is it unique, but the reverse query is also the same answer that if you look through B and you tried to find for each B which index in A, which number in A is closest. Yeah, the answers from A to B are the same from B to A, which is kind of why I was trying to figure out an answer for all numbers, for every index, what the answer is for like all the possible words you could pick from that are not unique, that have some duplicates. I want to say there's some kind of like a graph searching. Somehow you can make an analog to a graph with this question. Something. It's got to be something. Things get kind of funky when you're dealing with duplicates. It really does. It really gets funky when you're dealing with duplicates. Yeah, I'm like really struggling here. I am struggling here. Take the headset off for a moment. Still thinking. You know what? It's taking me so much time to think about this. I have to remember, every time I look at these questions, I always do that where I kind of... Oh, wait a second. Oh, give me a moment to... give myself a headache here. Standing up too quickly. You know what I tend to do when I look at these problems? I tend to make them way harder than they need to be. I overthink it when a relatively easy answer works. So let me do that. So what can be done is you can memoize the solutions. I'll explain in a moment. Yes, I'll explain. So you can memoize the solutions, and what you end up with is the first time you search for a certain pair could be kind of expensive, but when you run that query again, you've already saved the answer, hence you get the same answer again. I'm just thinking you don't even need to memorize both answers. You can just do a check to see if you have string A and string B, make a tuple out of that, and then memorize based off that key, that tuple, and you can reverse that and just see if the reverse exists in the map. You don't need to store the answer with both keys. You can just store with one key, and then just check if the key or the reversed key, symmetric key, if you've already found the answer. And you probably could just do a brute force. You really don't need to do you really don't need to do what do they call that? You can do a brute force search. You don't need to do what's the word I'm looking for? Yeah, brute force with memorization. You don't need to do anything fancy, as I was describing. I was kind of like getting hung up on what you could possibly do. Also, wow, my hand. Whoa. Anyway, the air is kind of dry around here, and my hands basically like bleed. It's kind of crazy. But okay, so yeah, let me try to do it that way. We have two things then. There is private. Oops. I did it wrong twice. There we go. couple things. We want the so we want a few things. One utility, one tuples. We want a map, and we want an unordered map. Yeah. And so we want our memo. It's going to be a tuple, I don't know, a map of tuple of strings and then we want string tuple, and actually an integer, just the answer. And then we want a unordered map of string to an index, and yeah, this is going to be sort of S to index. I don't really know what to call this exactly. You have stringed index. Oh no, and actually it's a series of integers. It's a vector of integers. Oh, did I hit the insert button? I didn't mean to hit that. Yeah, I guess S to Y. String of indices. And you really don't need more than that. I think that's kind of it. So the pre-processing step is just we're not going to modify this at all. So we say for auto W in words, you're going to say S indices of W. It's the other way around. Yeah, I equals 0. I is less than words dot size. Increment I. And then we'll say string W equals words of I. Pushback I. And then we do something really straightforward. We say for these two words, const standard string reference word 1, same thing. Word 2, say sort of a base case, I guess we'll say. It's not really a base case, but it's just memoization check. Call it that. We'll have a key. So it's good to, excuse me, never mind, we'll just say key, and we'll just say, standard make pair, word 1, word 2, and we'll do key 1 and key 2. Say if count of key 1 or memo, could do both. Yeah, we say memo key 1 or memo of key 1. So where why did I only have 3? If memo count key 1, return memo key 1. If memo count key 2, return memo key 2. Key 1, key 2 memoization check. Yeah, that's fine. And then we're gonna say for int I equals 0, or rather, really it's for auto x in S2 indices of word 1. And really it could be just int max, you know. X S indices word 1, Y S indices word 2, X and Y, say standard min of ret equals the minimum of ret and x minus Y, absolute value. Stop inserting these things too. I don't know where my hand keeps hitting the insert button. I think it's in the bottom right. I keep hitting it on accident. Min ret standard value x and y. Yeah, okay. And then we say memo of key 1 is ret. Turn ret. Okay. Something like this ought to do the trick. see what we do. Compile error. Too few template arguments for class template map. Excuse me. Oh. Typo. There's gonna be a lot of typos. Oh, it's correct. Nice. Okay. Do we just go for it? I think so. I don't know. I'm scared. I don't want to just go for it. Yeah, I'll just go for it. Oh, got it. Done. Just spent like half an hour laying down thinking about this problem, and it was really not. That's what I'm saying, man. Like I spend way too much time thinking about stuff sometimes. Still faster than 45% too. Not the fastest. There's probably a faster way. I think the faster way would be to use. You could use a binary search inside here in this loop, and that would be faster. But I mean, is there really? Do we need to do that? Not really. No. That's it. That's it. How long were we doing this for? How long were we doing this for? Really, we were just laying in bed for most of this. An hour and a half. Oh man. Oh man. No kidding. No kidding. Well, okay. We got there. Let me, let me just think for a moment here. Yeah, so what I want to do is probably just end the stream here. Pretty simple. Pretty simple, the whole thing. All things considered. Yeah. Alright. Alright. In that case, yeah, let's go ahead and end it there. So, really could have done that a lot faster. Probably could have done that in like 10 minutes instead of an hour and a half. Okay. Okay. All right. Let's end that here then.